All right, welcome to part two of the relative and absolute age dating reteach. In this part, we're going to learn about the absolute age dating rules again, what absolute age dating is. We're going to go over the vocabulary extensively, two different ways. Finish up with talking about ICE cores, problem solve most missed questions, and then you should hopefully be prepared to do the retakes. The retakes should be posted on the Canvas. So you'll be able to take those retakes after you're finished with the reteaches. Please do not use notes or other helpful devices when you're doing this, but of course, in our extenuating circumstances, we're just going to be doing our best here. Without further ado, here we go. Starting off with absolute age dating, this is different than relative age dating. Relative age dating, you're putting things in order. Absolute age dating, you're going to find out how many years ago something happened. So you're actually measuring how long ago something happened using chemical processes. This is where the vocabulary starts to get weird, so I wanted to break it down. We're going to have three different radio words. We're going to have radioactive, radiogenic, and radiometric. So radio means radiation, and then the three different suffixes are going to make three different words. Active means it's happening now. Genic means it's formed from. So let's start with those two. For radioactive, that means that material decays. Decay means that it's going to turn into something else. It's going to decay to form radiogenic material. Now that's going to happen at a decay rate. The decay rate is constant for each type of radioactive material. So different radioactive materials will have different decay rates, but each material's rate is constant for that thing. For example, uranium-235 will have a decay rate that is different than uranium-238, but uranium-235 will always have the same decay rate. Carbon-14 will always have the same decay rate, but that rate is much, much different than the decay rate of those uranium isotopes I already mentioned. That decay rate in all instances is called the half-life. Half-life is the decay rate, that is the speed that a radioactive material will decay to form radiogenic material. You can use that speed and you can use the amount of radioactive and radiogenic material in a crystal to measure the age of that rock. That is called radiometric dating. Radiometric dating is a type of absolute age dating that's going to use radioactive decay to figure out how long ago something happened. So that's going to be all of our radio words. And this is important. Radiometric age dating is going to give you the age of a crystal that contains the radioactive and the radiogenic material trapped inside of it. That has an assumption built in. I want to unpack that briefly. So radiometric age dating is absolute age dating using radioactive decay. It gives the age of a crystal in a rock. This means that the rock needs to be the same age as the crystal in order to be able to extend that age to the rest of the rock that it's in. This means that you can use radiometric age dating or absolute age dating with specific types of rocks, but not others. For example, a crystalline rock like granite, other igneous rocks, the crystal is the same age as the rock. So you're good to go there. But you're going to run into problems if you try to absolute age date a sediment inside of a sedimentary rock. Sedimentary rocks like sandstone. Sandstone is put together from individual pieces of sand that have been cemented or lithified over a long period of time, millions of years. In this instance, the sand crystals, or the crystals that the sand is made out of, they're going to be much older than the rock, or older than the rock in general. Sometimes much, much older than the rock. In either case, these crystals are not the same age as the rock. These crystals are the same age as the rock. Therefore, you can use radiometric age dating to find the age of a crystalline rock like granite. You cannot use it to find the age of a sedimentary rock like sandstone. Now that was a lot of words, so I want to go over these one more time in a very slightly different way using a table. See if this helps us get our brain organized. So if we have three three things that we're describing. We've got the material that goes away or decreases over time. We've got the way that that material is transformed or how we describe that transformation. We have the material that accumulates or increases over time. The unstable material becomes a stable material, saying the same thing with different words again. A radioactive isotope is going to decay to form a radiogenic isotope. Or, to say this a third way, a parent atom turns into a daughter atom. And all three of these, we have the transformation. The transformation is going to happen at a speed or a decay rate, and that is your half-life. Now that's the absolute radiometric age dating. Next up is the ice cores part of absolute age dating. And at ice cores, we need to keep track of what we have. So we're looking at a tube of ice that's drilled out of a glacier. Here we've got this ice field in the background. This tube of ice was drilled out of that. Here it is being preserved and photographed with some nice backlight to make the layers pop out. Ice cores will contain a few different things. Number one, they contain ice. Duh. Ice is made out of water, and that's actually really helpful for us because of what the water is made out of, not because of the water itself. Second thing that it has air bubbles. See these little air bubbles in it? Those air bubbles are going to contain oxygen and carbon dioxide from the time that the ice was formed. The last thing that they contain is volcanic ash or dust. And so let's go through their uses. The ice and the carbon dioxide that's in the air can both be used to get information about past climates. This is how we make our thousands of years models of what the Earth used to be like 400,000 years ago. As we find a glacier in Antarctica called the Vostok Glacier. We drilled a tube through it. We did not. The Soviet Union did. And we're able to measure the oxygen isotopes all the way through that ice core, measure the amount of carbon dioxide all the way through that ice core. And so we find that evidence of past climate that way. The other thing that we have is air. So we can actually use that air to directly measure what the atmospheric conditions were like when that ice was formed. That is a fossil or a preserved remain of that atmosphere at that point in time. You can do some actually fairly simple lab techniques because it's only ice that we're dealing with here inside of a vacuum conditions to try to measure that atmosphere without getting our atmosphere in the way. Vacuum means that you remove all the air from a container. So any air that's in there would be from the ice that's melting. Last thing is the volcanic ash. You can actually date that volcanic ash using radiometric age dating. Find out how old it is. That'll give you points in time throughout your glacier or your ice sheet. So that's what you can get out of ice cores, and that's how they relate to absolute age dating. So that last bit right there. Moving on from there, because that's the end of the review information, let's look at the most missed questions. We're going to look at question 5, 2, 4, and 7. After that, we had 75% or higher success rates. They're not really worth talking about because we didn't have big problems with them, but we had big problems with question 5. So let's take a look at this. What characteristic of carbon-14 dating helps scientists determine the approximate time a species became extinct? The only important part here is that's carbon-14. So if it's carbon-14, then that's going to be radioactive age dating or radiometric age dating, which means that the carbon-14, that's radioactive. They'll never, ever, ever describe a dating technique using its radiogenic daughter. They will only ever describe a dating technique using either the pair of parent and daughter isotopes or just as the radioactive isotope. You wouldn't say, I'm going to do nitrogen-14 dating because the carbon-14 turns into nitrogen-14. It's just not how that's just not the grammar of science. Anyway, we're talking about radioactive stuff. We are not talking about fossils. So that's right out. Carbon-14 is radioactive, so it goes away over time. This is saying it's increasing over time. This one says it goes away over time, which I'm pretty happy with that one. Let's just check the last one here. It's found in fossils of a certain time period. Once again, not talking about fossils. We're talking about carbon-14. That means the answer, letter C. Next up, which data is most likely to be obtained by studying ice cores? Ice cores are made of ice. Ice is going to contain the water, but we care about the oxygen isotopes, not the water. It contains air bubbles. It contains volcanic ash. So let's see what we have here. We have minerals in the geosphere. This isn't really true. That's not going to be in ice except for the volcanic ash, and that's really not going to be all the rocks on Earth. Hydrosphere. So we have the hydrosphere. So we have the water in the ice cores, but the water is not the important part there. The oxygen isotopes are. Oxygen concentration. The air that's trapped would have that. That's the correct answer there. Next up, radiometric age dating. For radiometric age dating, we are looking at radiometric, which means it's a type of absolute age dating that uses radioactive materials. You can come in. So that's the answer. It's not about relative age dating, it's not about fossils, and it's not about the surface of the Earth. That's just about absolute age dating. So that was the definition question. The last one is about sedimentary rocks. I do not think that we went over this in detail during our lessons for the week, and for that I apologize. But we've corrected that error in this reteach, and hopefully we don't make that same mistake again. Taking a look at this, we've got our sedimentary rocks. It's not working on them. It doesn't work on them because the crystals are older. So which one of those says that? Sedimentary rocks are too old? That's not it. Sedimentary rocks are made of small pieces of other rocks. Look at that, of crystals that are older. Makes the rock look older. That seems very consistent. Let's just make sure we have once living matter. That's not it. And sedimentary rocks do not contain isotopes. Everything contains isotopes. All an isotope is describing the atomic mass of an element. So it must be this one. That is the correct answer, and that is the last of the most missed questions. I hope that this is a helpful recap of the information that we need to know about absolute age dating, as well as what went wrong here. Please take a moment to review this again if you need to. Pause, back up, replay as much as you want, and then once you are comfortable, once you are confident, once you are prepared, then I would like you to try that retake, Mr. Hall's design, and post it on Canvas. Thanks.